Welcome to Academic Avengers. Today we're diving into an incredible topic, the different fields of physics. Now, before we get into the specifics, let's take a step back and think about what physics actually is. Physics is the branch of science that deals with understanding the nature and properties of matter and energy. It's like the ultimate detective work of science, trying to figure out how the universe works, from the smallest particles we can't even see to the largest structures like galaxies and beyond. So today, we're going to explore this library of physics and take a look at some of the most important fields, both from the past and the present. To make things easier to understand, we'll break it down into two main categories: classical physics and modern physics. Classical physics deals with the big ideas that were discovered before the 20th century, focusing on things like motion, sound, light, and heat, basically everything you experience in everyday life. Modern physics, on the other hand, digs deeper into the mysteries of the universe. It deals with the very small, like atoms and subatomic particles, and the very large, like galaxies and black holes. This is where things start to get weird and exciting, because we'll talk about concepts that challenge our everyday understanding of reality, like quantum mechanics and relativity. But it's not just about dividing physics by time periods. We can also think about physics in two other ways. One, theoretical physics, where scientists build mathematical models to explain how the universe works. Two, applied physics, where these theories are tested in experiments or used to create new technologies, like your smartphones, medical devices, or even space exploration tools. As we go through these fields, you'll notice there's often overlap. For example, what's the difference between astronomy, astrophysics, and cosmology? Even experts debate about this. So don't worry if it feels a bit confusing at first. All right, that sets the stage. Let's get started by diving into the first big area of physics, classical physics. Classical physics forms the bedrock of everything we know in physics today. It's like the foundation of a building. It supports all the modern ideas that have come later. Classical physics covers the period from ancient Greece, where philosophers like Aristotle were pondering the natural world, all the way up to the late 19th century, right before the start of the 20th century. So, what does classical physics study? It focuses on the everyday physical phenomena that we can see, touch, and experience. Imagine things like the motion of a car, the heat from a stove, or the sound of a guitar string vibrating. Let's break down some of the key fields within classical physics. 1. Mechanics. Mechanics is probably the oldest field in physics, and it's the one that most of you have already heard of. This is the study of motion, how and why objects move the way they do. It's divided into two parts: kinematics, which deals with describing the motion of objects without worrying about what causes that motion. Think about how we describe the speed of a car or the trajectory of a thrown ball. Dynamics, which is concerned with the forces that cause motion. This is where we talk about Newton's famous laws of motion. For example, why do you feel a force pushing you back into your seat when a car accelerates? That's Newton's second law in action. Mechanics has practical applications everywhere. It's what allows engineers to design bridges, architects to build skyscrapers, and athletes to perfect their movements in sports. 2. Electromagnetism. Next up is electromagnetism, which studies the relationship between electricity and magnetism. You might have learned that these two are closely connected, and this was a revolutionary discovery in the 19th century. Imagine you have a magnet and a coil of wire. If you move the magnet, you create an electric current in the wire. This principle is behind how we generate electricity in power plants. Electromagnetism is responsible for a huge part of our modern technology. It explains how electric circuits work, how light behaves, and even why your smartphone can wirelessly charge. 3. Optics. Another important field in classical physics is optics, the study of light. Light is a special type of wave, and optics explores how light behaves when it passes through different materials. Have you ever noticed how a straw looks bent when it's in a glass of water? That's due to refraction, a key concept in optics. It's why lenses and glasses can correct your vision, and why we can build powerful telescopes to look deep into space. 4. Thermodynamics. Let's move on to thermodynamics, which deals with heat and energy. This field looks at how energy is transferred and transformed. For example, Why does your coffee get cold if you leave it out? It's because heat energy is spreading out into the cooler air around it. Thermodynamics gave us the concept of entropy, which is a measure of disorder. It's why everything in the universe tends to move from order to chaos, like ice melting into water. The laws of thermodynamics are fundamental and apply to many areas of life. For instance, they're used in designing engines, refrigerators, and even understanding the life cycle of stars. 5. Acoustics. Lastly, we have acoustics, the study of sound. Sound is another type of wave, but instead of being a wave of light, it's a mechanical wave that travels through air, water, or solids. Have you ever wondered why your voice sounds different underwater? That's because sound travels faster through water than through air. Acoustics has applications in designing concert halls, creating noise-canceling headphones, and even studying earthquakes, which produce sound waves called seismic waves. So to sum up, classical physics laid the groundwork for everything we know today. It covers the motion of objects, mechanics, the behavior of light, optics, the properties of heat, thermodynamics, the mysteries of electricity and magnetism, electromagnetism, and the study of sound, acoustics. These fields help explain many of the natural phenomena we see around us every day. Now, as we move forward in time to the 20th century, scientists began to notice that classical physics couldn't explain everything. There were mysteries at the atomic level and in the vast reaches of space that didn't fit these classical laws. This brings us to the next part of our journey, modern physics, where things get a lot more interesting and a bit strange. Modern physics. Now that we've laid the groundwork with classical physics, it's time to dive into the more mysterious, mind-bending realm of modern physics. While classical physics does a great job of explaining everyday phenomena, it starts to break down when we look at the tiniest particles or the most extreme conditions, like near the speed of light or at the edge of a black hole. In the early 20th century, scientists like Albert Einstein, Niels Bohr, and Werner Heisenberg began exploring these new areas. They uncovered strange, unexpected behavior that classical physics couldn't explain. This led to the birth of modern physics, which focuses on understanding the subatomic world, the nature of space and time, and the fundamental building blocks of the universe. Let's explore some of the most important fields within modern physics. 1. Quantum mechanics. Let's start with the most famous and perhaps most puzzling area of modern physics, quantum mechanics. If classical physics is the study of the big, everyday world, then quantum mechanics is the study of the very small, where things get weird. Here, particles like electrons and photons don't behave like solid objects. They behave more like waves. Even stranger, they can exist in multiple states at once, a concept known as superposition. You might have heard of Schrödinger's cat, a famous thought experiment that illustrates this weirdness. Imagine a cat in a box with a radioactive atom that has a 50% chance of decaying. If the atom decays, the cat dies. If it doesn't, the cat lives. According to quantum mechanics, until you open the box and check, the cat is both dead and alive at the same time. It's a bizarre idea, but it's fundamental to how particles behave on the quantum level. Quantum mechanics is not just a theoretical concept. It's the foundation of technologies like lasers, semiconductors, and quantum computers, which are set to revolutionize the tech industry. 2. Relativity. Next, we have relativity, another groundbreaking area introduced by Albert Einstein. There are two parts to this theory. Special relativity. This deals with objects moving at high speeds, close to the speed of light. One of its key concepts is that time and space are relative, meaning they can change depending on your speed. For example, if you were traveling in a spaceship at nearly the speed of light, time would pass slower for you than for someone standing still on Earth. This is called time dilation and has been proven through experiments. General relativity. This is Einstein's theory of gravity, which describes how massive objects like stars and planets bend space and time. Imagine space-time as a giant rubber sheet. When you place a heavy ball on it, the sheet bends. This bending is what we perceive as gravity. General relativity helps explain phenomena like black holes, where gravity is so strong that not even light can escape. Relativity has practical applications too. For example, your GPS system wouldn't work without corrections from relativity because time moves slightly faster for satellites orbiting the Earth than it does on the ground. 3. Particle physics. Now let's zoom in even further with particle physics, also known as high-energy physics. This field explores the fundamental particles that make up the universe, like quarks, leptons, and bosons. If you've ever heard of the Large Hadron Collider, LHC, at CERN, this is what it's used for, smashing particles together at incredibly high speeds to discover what they're made of. A key part of particle physics is the Standard Model, which is like a periodic table for subatomic particles. It includes particles like the Higgs boson, which was famously discovered in 2012 and helps explain why particles have mass. This field aims to answer some of the biggest questions in physics, like what are the building blocks of the universe, and how do they interact with each other? 4. Astrophysics and cosmology. Moving from the very small to the very large, we have astrophysics and cosmology, which study the physical properties of the universe. While classical physics gave us basic astronomy, modern physics digs much deeper. Astrophysicists study stars, galaxies, and phenomena like black holes and neutron stars, where the laws of physics behave differently due to extreme conditions. Cosmology, on the other hand, focuses on the universe as a whole, including its origin, evolution, and fate. It's the study of the Big Bang, dark matter, and dark energy. Did you know that only about 5% of the universe is made up of normal matter like atoms? The rest is mysterious dark matter and dark energy, which we still don't fully understand. 5. Quantum field theory and string theory. Lastly, we have fields like quantum field theory and string theory that aim to unify all the different forces and particles we know about. Quantum field theory combines quantum mechanics and relativity, explaining how particles interact through fundamental forces like electromagnetism. Meanwhile, string theory suggests that all particles are actually tiny vibrating strings, and the different vibrations determine the type of particle. Although string theory is still very much theoretical and has not been proven, it offers a possible path to a theory of everything, which could unify all the laws of physics into a single framework. So, to sum it up, modern physics has opened our eyes to a whole new world of the very small and the very large. It challenges our everyday understanding and has led to groundbreaking discoveries. Quantum mechanics explores particles on the atomic scale, revealing strange behaviors. Relativity redefines our concepts of space, time, and gravity. Particle physics digs into the fundamental building blocks of the universe. Astrophysics and cosmology explore the origins and behavior of the universe on the largest scales. Modern physics is not just abstract theory. It has practical applications that impact our daily lives, from electronics and medical imaging to our understanding of the universe's origins. This concludes our journey through the fields of physics. I hope this gives you a better appreciation of how vast and diverse the study of physics really is. Now, let's open it up for questions. What would you like to know more about? Conclusion. So, to wrap things up, physics is the study of the natural world, from the tiniest particles to the vast expanse of the universe. We explored the foundations of classical physics, covering forces, motion, and energy, which help explain our everyday experiences. Then we journeyed into modern physics, where things get stranger, diving into the realms of quantum mechanics, relativity, and the fundamental particles that make up everything around us. Physics isn't just about equations and theories. It's the key to understanding how the universe works, driving technology and innovation. Whether it's through your phone's GPS, medical imaging, or the study of black holes, physics touches every aspect of our lives. So, next time you look up at the night sky or think about the tiniest atom, remember, it's all connected by the laws of physics, and we've only just scratched the surface of what's possible. Thanks for watching. Check back every week for new videos, and don't forget to like, subscribe, and comment down below.